Welcome to this explainer. If you've been working in software over the last couple of years, you've definitely felt it, right? We've gone through this massive shift. AI coding assistants, stuff like Claude, GitHub Copilot, and Cursor, have completely moved past that novelty autocomplete phase. Today, they're active participants in the development process. We're talking about tools that can write functions, debug failing tests, refactor entire files, and even execute multi-step tasks with minimal human input. But to truly leverage them, we need to cut through the marketing hype and understand the actual mechanics of how they work. Okay, let's dive into this because this right here is the central thesis of our entire explainer. AI-assisted engineering doesn't eliminate the need for engineering skill. It raises the cost of not having it. That's huge. This isn't about replacing engineers. It's about shifting how we apply our expertise. As we'll see, the tools are incredibly powerful for sure, but relying on them blindly is an absolute recipe for disaster. So here's our roadmap. First, defining the paradigm. 2, going under the hood. 3, real strengths and limitations. 4, the judgment imperative. And 5, a realistic daily workflow. Number 1, defining the paradigm. What it is and honestly, what it isn't. Look, there's a really sharp line between traditional hand coding, human-directed AI-assisted engineering, and the hype around completely autonomous software creation, what some folks playfully call vibe coding. With AI-assisted engineering, you, the human engineer, are still entirely on the hook for the architecture, the correctness, the security, and making sure the software actually solves the right problem. The AI doesn't understand your business problem the way you do. It just doesn't. It simply generates the most statistically plausible next piece of code based on patterns. The actual engineering, the directing, the context, the intent, that still fundamentally comes from you. 2, under the hood, how the technology works. The bedrock here is pattern prediction. Large language models are trained on just immense amounts of text, public repositories, and documentation. The model learns statistical relationships between tokens, which can be words, symbols, or code fragments. So when you give it a prompt, it predicts a highly plausible continuation. But here is the critical catch. It is optimizing for plausibility, not verified correctness. That is exactly why the output can look incredibly fluent and super confident, even when it's factually or logically completely wrong. Now, lifting the hood on the source material here, we can see the supporting structures around the LLM. It's not just a text box anymore. To make that pattern prediction actually useful for software development, the surrounding architecture has to bridge the gap between a generic model and your specific, unique code base. And that brings us to context windows. An AI only knows what is placed directly in front of it during a given interaction. It does not possess some magical, persistent understanding of your entire project architecture. The prompt, the attached files, the previous messages, that is literally all it has. This is exactly why modern AI coding tools aren't built around assuming full project awareness. They're built around retrieving the right context. So how do they get that right context? Vector embeddings for larger code bases. These tools convert source code into numerical representations of meaning. This lets the AI search a massive codebase semantically. Instead of scanning every single file line by line, which would be impossible for the context window, it fetches the specific piece of code relevant to your request. So you ask for the function that handles user authentication, and the system retrieves exactly that context to feed the LLM. It's brilliant. And taking it a step further, we have agentic workflows. Modern tools go way beyond just generating text and stopping. They create an active loop. They can execute commands, run your test suites, read the error output when a test fails, and literally revise their own work based on what happened. This agentic loop lets the system catch some of its own mistakes, significantly reducing the friction of the drafting process. 3, real strengths and limitations. Let's talk pragmatics. When used right, the value is just immense. These tools are genuinely fantastic at generating boilerplate and repetitive scaffolding. They're great at explaining unfamiliar or legacy code. If the underlying logic is tightly defined, they can write comprehensive test suites fast. They translate frameworks easily, and most importantly, they drastically shrink that time it takes to go from a totally blank file to a working draft. But you absolutely have to respect the limitations. Put your senior engineer hat on for a second. The model will hallucinate APIs. It'll invent functions that sound perfectly logical, but simply do not exist. It has massive security blind spots, generating code that looks complete but hides real vulnerabilities. It lacks business context. It doesn't know your company's constraints unless you explicitly feed them in. And beware of compounding errors in long automated runs. If the agent makes a wrong assumption early on, it'll silently corrupt everything it builds on top of that mistake. So, the crucial point is this. The greatest risk is in the technology, its skill atrophy. If engineers stop actively reading and deeply understanding the code they're shipping, they completely lose the ability to catch those subtle, confident errors the AI introduces. Honestly, if you stop reading the code, you quickly become a liability to your team.
4. The judgment imperative.
I want to read this quote from the source directly because it just hits the nail on the head. A skilled engineer using these tools ships good work faster. An unskilled one ships bad work faster. The technology is a productivity multiplier. It amplifies your existing judgment. It does not and cannot substitute for it. Human review is a required step. It is not an optional add-on. Your role is shifting from being the author of every single mundane line of code to being the verifier and the architect. You have to review that generated output for logic errors, security flaws, and system design fit.
5. Realistic daily workflow. What does this actually look like?
And this brilliantly illustrates the day-to-day reality. It breaks down into a really structured dance between human intent and machine execution.
It builds into a practical 5-step loop. Step 1, the engineer clearly defines the problem and constraints. This is where your business context shines. Step 2, the AI drafts the code, a plan, or tests based on your definition. Step 3, the engineer reviews the output, runs it, and checks the edge cases. Step 4, the AI revises based on the real feedback, errors, or test failures you just found. And finally, Step 5, the engineer signs off. Notice how the engineer's judgment firmly brackets the AI's work at both the very beginning, the definition, and the very end, the sign-off. The AI handles the heavy lifting in the middle, but it has no way of knowing with absolute certainty if its own output is truly correct for your users.
Ultimately, AI-assisted software engineering is an incredibly powerful layer on top of traditional engineering practice. As these tools continue to improve, they will absolutely raise the ceiling on what you can build and how fast you can build it. But remember, human judgment still sets the floor on what is actually safe to ship. So as you integrate these tools into your daily workflow, ask yourself, is your judgment sharp enough and your review process rigorous enough to confidently set that floor? Thank you so much for joining me for this explainer, and I'll see you next time.